Module 10. We're going to be looking at gases. We see our little balloon there. It's going to get really big. I guess it's going to pop. I don't think it popped. Maybe it. So, yeah, there it is, right there. Okay, so remember, last time we concentrated mostly on liquids, yes? So now we're going to look at gases. Okay, keep in mind that all matter is moving somewhat, right? So our solids are moving just a little bit because they're so close together like that. The liquids are slipping past each other in a fluid motion, and the gases are just moving as far away from each other as possible. They're the most antisocial of the matter out there, yes? So they're moving away. They're going to fill up their container, whatever it is. Let's say that it's microwave popcorn that we smell, right? And somebody's burned it. It goes as far as it can. But each of those little gas molecules is hitting up against things, like the wall. If the container is this room, for instance, up against the wall. Right now we have a gas in this room. It's called air, right? And all those little molecules are hitting us. They're hitting the wall, all this kind of thing. And so keep that in mind when we start looking at our gases. Okay. So, first thing we need to know is that when we measure gases, when we're looking at gases, we're talking about something called pressure. So how do we measure pressure? What is it? The force per unit area exerted on an object. That's the definition you're writing down in your book. Joe?
I already done it. I did all this at home.
You wrote all these things down?
Most of them.
You want to pull it out and follow along?
Hayden copied off my book.
Gotcha. Well, Hayden, I hope he's right. I don't know. I didn't send him this, so. The 4 different units for pressure are these. Atmosphere. It's literally talking about how much the atmosphere is pushing down on us. Pascals, which is Newton meter squared. And we have a name for it called pascals, named after Monsieur Pascal. We'll look at him in a minute. Torr. We don't use torr very much, but except for in a mathematical problem, you might need to know that. In a minute, you're going to be writing down some of the conversions for these. And then millimeters of mercury, which is actually much more common than you might realize. And we'll see why on that for pretty soon here as well. So in general, our math equation would be that pressure equals force over area, literally over area, divided by area. We don't need to write down that math equation. We have several math equations today, but we're going to boil it down to 2 that we really need. But I'm going to take you a little bit through the history so you can see how we got there. All right, so our gas is in a little container, and like I said before, it's bouncing off the walls of the container, whatever that happens to be. Okay, so you may have some practice problems this week in your module that will deal with one or more of these. You may have to do some conversions. This is Monsieur Pascal. His name is Blaise Pascal. He was a philosopher, but his philosophy brought him over to the sciences, brought him over to math specifically, and he was able to see this beautiful design in nature. Now, he was just before the French Revolution, and so it... Pardon?
Did he get beheaded by any chance?
He was before that. Okay, so it was just before that. But if he had been during the time of the revolution, he probably would have been. So I don't know how wealthy his family was. So here's one of his very famous quotes. There is a God-shaped vacuum in the heart of every man, which cannot be filled by any created thing, but only by God, the Creator, made known through Jesus Christ. So he is definitely a believer. So everything he looked at that showed him all this beautiful order in the universe took him back to understanding it's because we have an orderly God. All right, so this is one of the smartest people ever to have lived, and he believes in God, so that's good, yeah?
Very nice.
All right, so what is an atmosphere? Let's start with an atmosphere. The gases exert pressure on any surface that it comes in contact with. We know that. This includes our atmosphere. So what we have is we have essentially a column of air coming down, and when it hits the surface, we have this thing called the pressure at the surface, and that is known as an atmosphere. Because it's an arbitrary term, it's something we've said, okay, we're going to give this a value. Very, very kindly, the great scientists of old gave us the value of atmosphere at the surface level of the earth is 1. All right, so when we put that in a math equation, it's just 1. And we're going to put everything else in relation to 1 atmosphere pressure. Now, of course, that's going to change depending on where on the earth you are, correct? This is the value of an atmosphere at sea level. Boom, okay? If you're in the mountains, it's different. You already know that. You know that the pressure, air pressure changes. It also changes due to our weather conditions. kind of cloudy out now, we have a lower pressure day. On a sunny, bright day, we have a high pressure day. So that pressure will change a little bit. We find that out by using different instruments, which we'll get to. All right, so these are the things we're going to need to know. One, for the pascals, when we're going to convert over to pascals, we're going to use kilopascals because it's such a large unit. So 1 atmosphere equals 101.3 kilopascals. That's named after, Mr. Pascal. In the torr, we have 1 atmosphere equals 760 torr. And we have 1 atmosphere equals 760 millimeters of mercury. We'll see why mercury was the one that was chosen. What do y'all know about mercury? The element, not the god or the planet. It's the only metal liquid at room temperature on the planet. It's the only one. So it's a liquid. And it doesn't evaporate very easily at all.
So
Okay.
if it's a liquid, then at what point does it become a solid?
It has to get really cold. I don't know its freezing point. We could pull out the chart of the elements and find out its freezing point. I'm not sure. I don't think it's I think it must be pretty low.
Yeah.
Because you know what we put mercury in? Thermometers. And we're going to see today it goes into something called a barometer. All right, so measuring pressure. One way of measuring pressure, so if I'm in a lab and I'm trying to get the pressure of a gas during one of my experiments, gases are hard to measure. They're hard to weigh. You can't weigh a gas very well, can you? So this is the whole reason we're going to be looking at these math equations today, is because we're going to look at the way to figure out what's going on, or even the mass of a gas, by knowing everything else about it, knowing its pressure, knowing its moles, this kind of thing. And this is called a manometer. And a manometer has a tube like this with either water or mercury in it, typically mercury. And I can put gas in. There should be a little device over here where I could squeeze, push gas into it. Let's see, I'm going to push helium into this little glass bulb right here. And it's going to push on this and push it up, and we're going to see the change that it makes in there depending on how much I put in. And I'll be able to measure the pressure of the gas. And then I can use that pressure to figure other things out about the gas. Or gases. Sometimes we have more than one gas in there. A barometer you're probably more familiar with. Okay, so a barometer is using a bowl full of mercury, liquid metal, and an evacuated tube right here, and the air pressure will push on the mercury, pushing it up the tube, and so my mercury can be rising or my mercury can be lowering. That'd be a rising air pressure or lowering air pressure. Okay, and that would be atmospheric pressure. Let's watch a little history of the barometer.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist, because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top, and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
Alright, so the idea there is the pressure pushed by the air by the gases. Okay, so we're going to be looking at these gases. In the mid-1600s, Robert Boyle, Boyle's an important name, we're going to have this law called Boyle's Law, created a vacuum pump. Now that they know vacuums are something, the exact quote is, nature abhors a vacuum, it hates a vacuum. And so, but now it can be done. He established this fact that P times V, so pressure times volume, was always constant. Now this isn't exactly the math equation you're supposed to write down. Yeah, not yet. Don't do it yet. Because it's not really giving us very much information. It's giving us the concept. When the pressure of a gas increases, the volume will always decrease. When the pressure of a gas decreases, volume will increase. All right, so he did a bunch of work on this, testing this this theory of his, right? He had this theory, and over time it was tested and retested till it was so well founded that it became a scientific law. All right, it takes a lot to become a scientific law. And so if we have something we can really attribute to somebody, we give it their name, so we gave it back to Boyle, Boyle's Law. All right, this is Mr. Boyle's quote. "What an almightiness is eminently displayed in God, making out of nothing all things, constructing this immense fabric of the world, whose vastness is such that even what may prove of it can scarcely be conceived." Once again, a guy who, when he looked and saw this stuff and saw this order, he realized it was due to the creation of an orderly God. So here's his law. This is, I want you to see in these two pictures right here, this red thing is a piston, and the piston can be moved up and down and change the amount change the volume and change the pressure. Here we have 3 weights on there, so the volume's at about 4 right here, the pressure at 1. The pressure's increased, 1 more weight is added, and it squeezes the piston, it pushes the piston down, and the volume is at 3 now. At this particular experiment that Boyle did, it was always very important to him to limit his variables, and one of the variables, of course, would be temperature. And so he kept the temperature the same. He was very careful to keep the temperature the same, whatever that was. All right, so we're going to see here what happens when we put a gas under pressure. Okay, you can see, we're going to see the piston moving. Those are those gas molecules. Notice their volume is getting smaller. Their pressure is increasing. The volume is getting smaller. What else do you notice about them?
They're getting much closer together.
They're getting closer together. They're going faster. Notice the color change. So what do you think's happening? What does that color change mean?
Increasing temperature.
They are heating up. The gas is heating up. We're going to see that in just a minute, how that takes place. All right. So the alternative way of stating Boyle's law is this. This is what you're writing in that little box. P1 for pressure, V1 for volume equals P2, V2. So when one goes up, the other will go down. One by side, versa. So yeah, that's Boyle's law right there. So another guy comes along and says, very interesting, Dr. Boyle. His name is Charles. His name is Jacques Charles, and he experimented using temperatures. He said, okay, you kept the temperature constant. What if I mess with the temperature? What is going to happen then? And he found out this, that volume and temperature is always volume over temperature is always constant. All right, so he found out this was linearly proportional. At a constant pressure, if he was able to keep the pressure constant, the temperature and volumes are going to change based on changing one of those variables. All right, so if the temperature is lower on the left side here, you can see that our volume is at V1. All we do, now this piston right here is fixed. In other words, it can move, but he didn't move it. All right, so it's going to move on its own, right? So as far as, so the pressure remains the same. And so we raise the temperature, what happens to the volume? It gets bigger.
Which makes sense because last week we learned that if you cool down a gas, then it moves less and shrinks.
And it shrinks, right. And we'll do that for our lab next week, yeah. Okay, in 1700s, Jacques Charles added the component of changing temperature to the study of gases. So this is our equation, V1 over T1 equals V2 over T2. And you see here, at a low temperature, my balloon is small, and a higher temperature, the balloon expands. So that's the one, you know, no, I'm not going to write those down. Yeah.
Could you heat it up so much that the balloon would like pop?
Yes, you could. So it really depends on the material, right? So you got to be careful. So there, we'll see a picture here in a little bit that shows a balloon with a candle underneath it. I'm like, okay, well, how well is that candle going to do with that? How well is that balloon going to do? It's going to pop from the heat of the candle. It's going to burn a hole in it or whatever.
Instead of just being
So at a constant pressure, the temperature and the volume of the gases are linearly proportional. If the temperature of the gas is double, the volume doubles. If the temperature is halved, the volume of the gas decreases by a factor of 2. All right. We're going to try this experiment next week, hopefully.
Today on Sci Guys, microwaving ivory soap.
Welcome to Season 4 of the Sci Guys. I'm Ryan.
And I'm Mark, and on today's episode, we'll be microwaving ivory soap.
Mark, we made it to Season 4.
I know, I should
High
high
five.
five. No, watch the elbow.
Oh,
Watch the
elbow?
elbow.
Hey!
Charles's law states that the temperature and volume of an ideal gas are directly proportional. What this means is that as the temperature goes up, so too does the volume, and vice versa.
The equipment you're going to need for this episode includes a microwave,
Soap, specifically Ivory brand,
and a paper towel or microwave safe plate.
the safety equipment we recommend for this experiment include gloves, goggles, and an apron or lab coat. Also, the plate will be very hot at the end of the experiment, so for our younger viewers, we recommend getting the help of an adult. All you have to do for this experiment is take your soap, put it on your microwave safe plate,
And put it in the microwave for 2 minutes on high. A short time after you start your microwave, the soap will begin to grow and expand. It will continue to expand over the course of the 2 minutes that it's in the microwave. Remember that once the microwave is done heating our soap, the soap and the plate will be really hot. Give them a few minutes and then use heat-resistant gloves to remove them from the microwave. Once the soap is cooled, you should now have a large pile of fluffy soap. Let's look at this experiment a little closer. When ivory soap is made, its soap mixture is whipped together, which causes lots of air molecules to be trapped in the soap. These trapped air molecules allow ivory soap to float in water, and they are the main reason why the soap will expand when heated in the microwave. Microwaves produce alternating electromagnetic waves. Once these waves reach the soap, they excite the water molecules in the soap, causing them to vibrate faster and rise in temperature. This rise in temperature softens the soap slightly and heats up the trapped air molecules. As the water and air molecules heat up, they spread further apart, increasing the volume and pressing against the warm, soft soap molecules. The expansion of the water and air molecules is a great example of Charles's law of gases. Charles's law states that when a fixed amount or mass of an ideal gas is kept at a constant pressure and in a closed system, then its temperature and volume are directly proportional. What this means is that when temperature increases, volume increases, or as temperature decreases, volume decreases. The warmer the air molecules get, the further apart they spread, pushing outwards on the soap, causing it to grow and expand into a fluffy white mess.
Well, that's it for microwaving ivory soap. Thanks for watching.
If you enjoyed this episode, let us know in the comments.
So it's not really a mess when it's done. It'll leave the kitchen smelling all soapy clean. Yeah. So, and it's also not fluffy. It's solid. Yeah. So pretty cool. All right. So that was showing how the temperature was increasing and the volume was increasing. That's the linear portion. Okay. So if we see right here, we're going to look at several gases. We're going to see what happens to them with the temperatures. Here, as they go up, starting from this, this is temperature in C, -100. Up this way, you're going to see we have a line on our graph right there. So our data points would end up making that line that goes straight up like that. And then Charles tested lots and lots of different gases, and they all did that on their own trajectory, but definitely making that line like that. Notice this dashed line right here. We call that an extrapolation, and that's because it's kind of difficult to get cold down here, which brings us to the third law of thermodynamics, which states that we cannot reach absolute zero. Absolute zero is 0 Kelvin. We can't get there. It's impossible. It breaks the law of thermodynamics. Okay, it is the temperature of space, but on the planet Earth we can't get there. We can get close using some fancy equipment, very expensive equipment, and get close, but we never have been able to get to absolute zero. All right, so now we've taken all those two equations you have so far, we can throw those out. We don't need those because we're going to combine them and use this more useful one right here. We're going to combine the gas. It's called the combined gas law. We're going to combine Boyle's law and Charles' law to get P1 V1 over T1 equals P2 V2 over T2. All right, we're going to need that here in a couple of math problems. Okay, and you should have some practice problems this week to work on that'll use this formula. And we're going to move on from here in the second half. Okay, common rearrangements, if y'all want to write those down, I just say we do the math at the time and figure out what our need is. But if I'm looking for P2, it's going to look like that. If I'm looking for V2, it's going to look like that. I will tell you up here like this, we can have cancelings. We can cancel some things out when we rearrange like that, okay? So we can cancel out different things. Okay, and also we have to use the Kelvin scale. Now here's the reason we have to use the Kelvin scale. What's on the bottom of our fraction? Temperature. If I'm using the Celsius scale, might that sometime be 0? Can we have a fraction with 0 on the bottom? No. Okay, we can't. That's irrational. Is it irrational? Is that what it's called? The irrational number?
Yeah, we can't divide by 0.
You can't divide by 0. And so therefore we must use, and we can never get to absolute 0. That's the third law of thermodynamics, right? So therefore we're always going to use the Kelvin scale. So here's the question. Typically when I give you a problem, it's going to have it in the Celsius scale, and so we need to convert it. So you need to write this down. If we have our C, our Celsius, our K, getting to Kelvin, which is by the way named after Lord Kelvin, plus 273.15. So we're just going to take the number we're given, we're going to add 273.15 to it, and that's going to be the number we're going to use for our math equation.
So basically you'll never get -273.15 in Celsius.
I guess, right.
Absolute zero.
Right. So, however, yeah, that's it'll never be down here to the 0, yeah. Okay, so example, I think 0, that's 0 degrees Celsius. Example 11.1, here we go. Here's our first example. I think there's a box for you to write this in. A weather balloon is filled with helium before it is launched. On the ground, it has a gas. The gas has a temperature of 25 degrees C and a pressure of 1 atmosphere. The volume is 4.5 cubic meters. As the balloon rises, the pressure and temperature change to 0.30 atmospheres and 15 degrees C. What is the new volume of the balloon? All right, so we're looking for V2, right? Yeah, we're looking for V2, but the first thing we're going to do is convert our temperatures, okay? So we're going to convert to Kelvin. I have T1 is 25, which was given to me, plus 273.15 gives me 298 K. That's T1. And then T2 is 15 degrees plus 273 right there is 288. All right, so now we can solve for V2. So V2 is going to be P1 V1 T1 over T1 P2, and we're going to see our atmospheres were given to us, our volume, our temperature, and our pressure that were all given to us right there. Okay, that's all. The only really work we had to do was this, and then remember this equation right here. And we end up with 14 cubic meters. So the volume got much larger, right? The volume went from 4.5 cubic meters to 14 cubic meters, which brings us to the reason why we put helium in balloons in weather balloons. Okay, so the reason we do that is we send up a weather balloon. It's got helium, it's going to go up, it's got a box that's gathering information up in the upper atmosphere, and then at a certain place the volume of the balloon's going to get so big, what's it going to do? It's going to pop. And then we have a little, that's a what do you call it, parachute? And then you saw briefly right there the little box with the data collector right there. You saw the little data collecting. Then that comes down to the earth and we collect it and we look up the data and find out what's going up in the upper atmosphere. We actually still do this, although we've changed a lot of this to satellite data that we collected. All right, a gas is stored in a metal, guys, a gas is stored in a metal cylinder with a volume that cannot change, fixed volume. All right, so what do we know about volume then? It's not going to change, and I think this is the one where we can end up just canceling volume in our math problem. Yeah. If the gas is packed into a cylinder at a temperature of 5 degrees Celsius and under a pressure of 3.115 kilopascals, pascals, what will the pressure be when it is stored at 30 degrees C? All right, so this could be something like when they bring my liquid propane to me, have it under liquid, and it's going to be able to get out and become a gas, because by the time it gets to my house, it becomes a gas.
Would
Right?
you have to change it into atmospheres, or could you just leave it in
I think we
kilopascals?
have to change it into atmospheres. Let's see.
Doesn't
Solving
say.
for P2, that's what we're looking for. So here we have P2 equals P1 T2 over T1, because the volumes canceled out, because they didn't change. All right, we're going to convert to K first. We see T1 and T2. And here we go. It looks like we can say with kilopascals. We'll just keep it at kilopascals. So there's our math, all those numbers. And that was our answer. Do you want to write that down?
Yes.
Okay. So as long as the units all agree, we're fine with not changing them. Eventually, I know we have one we're going to have to convert pascals. Our question here was looking for the pressure, and that is at kilopascals. And this is a on your own, one of the on your owns. Okay, so now we're going to talk about all this stuff I told you is only true under certain conditions. So it's really not exactly true. It's only true under ideal conditions. Okay, so we have something called the ideal gas, which leads to something known as the ideal gas law. All right, what properties make a gas ideal? Number one, the molecules or atoms of the gas are small. So here for number one, look, I put small number. That's all you have to write in there, small number. Compared to the total volume available, there's only a small number of molecules or atoms. Number two, the molecules or atoms of the gas are so far apart there is no attraction or repulsion between them, so you can write in they're far apart. Atoms and molecules are far apart. And number three, they have elastic collisions. And what that means is when they hit against the wall, they hit against me, they hit against whatever, there's no energy lost because there's enough room for them to bounce, just like bouncing balls. I think the book used the example of billiard balls, and I'm thinking they probably lose a little energy when they clash together like that, you know. So I think more like a, you know, I don't know, they're slowly bouncing, if you will. But you can just write down elastic collisions. They bounce without losing energy. We're going to also see that this is all very true when we have at particular temperatures. All right, so we'll get to that. All right, now the conditions for ideal gases. Higher temperatures are better, lower pressures are better, And we have something called standard temperature and pressure, STP. STP is important. We're going to encounter this again in another place, and it's going to be talking about something totally different. So, yikes. STP is for two things. All right. So at 273.15 K or 0 and 1 atmosphere pressure is this, that's STP. So what is STP? 273.5 Kelvin or 0 degrees C and 1 atmosphere pressure. So you'll be reading, like for instance, a problem that says using STP calculate la la la. So you're going to have to remember, okay, that's 1 and 0 or 273. Okay? You have to remember, it's going to be an assumption you understand what STP is. So STP, 1 atmosphere and 273.15 K. All right. Now we're going to look at what happens when we mix gases together. So we're going to be looking, remember John Dalton? John Dalton is the one that came up with the atomic model, right? Not the model, but the atomic theory of atoms and how they work. So he also has this Dalton's law of partial pressure. And what he's saying here is when I mix gases together, my pressure 1 of gas 1 plus my pressure 2 of gas 2 is going to be a total pressure of gases 1 plus 2. Addition. It's tough. Yeah, it's a tough problem here. All right, so we can see right here I have oxygen at 159 millimeters of mercury. That's the pressure unit being used here. They're using that gauge. Then I have my nitrogen with 593 millimeters of mercury. I mix them together, and my pressure is 752 millimeters of mercury. And 159 plus 593 equals 752. Okay? That's all that's saying right there. So, what do we do with it? When two or more ideal gases are mixed together, notice it says ideal. We're going to assume that on your problems. The total pressure of the mixture is equal to the sum of the pressures of each gas. What if I have 15 gases? Add all 15 together. Okay? But pressure total is pressure 1 plus pressure 2 plus pressure 3, etc. Here's our first question. A steel drum is holding 5 atmospheres of nitrogen gas. A chemist adds 5 atmospheres of oxygen gas. What's the resulting total pressure? 10. That was a tough one. All right, so y'all want one of these on the quiz? A couple of these on the quiz? Yeah. All right, let's watch the video.
Fill down this quiz specifically, would you?
Let's say we have a container with 3 different gases. Gas 1, gas 2, and gas 3. Note that the gases are all inside the same container. This means that they all have the same volume. Now let's take the same container and spread the gases out equally while holding the volume constant in each container. The sum of the partial pressures of the 3 gases will equal the total pressure of the mixture of gases. Let's look at the pressure meters above the gas chambers to notice that each partial pressure of the individual gases equals the pressure of all the gases in the same container. Now let's look at the formula for Dalton's law of partial pressure. First, let's derive the ideal gas law, where pressure times volume equals nRT. We can see that the pressure is equal to nRT over V. Now let's look at Dalton's law of partial pressure, where at a constant volume, we can add the partial pressure volumes of the individual gases to equal the total pressure of the combined gases. Let's do a sample question here. A gas mixture contains hydrogen, helium, neon, and argon. The total pressure of the mixture is 93.6 kilopascals. The partial pressures of helium, neon, and argon are 15.4 kilopascals, 24.7 kPa, and 35.6 kPa respectively. What is the pressure extended by hydrogen? So we know that the total pressure is equal to 93.6 kilopascals of pressure, and we have the pressures of the other 3 gases in the mixture. We also know that all the units are the same, and we don't have to do any mole conversions. So all we need to do is add up the 3 individual pressures and subtract them from the total to get the pressure of hydrogen, which is 16.9 kilopascals. This question uses Dalton's law of partial pressures perfectly. Thanks for watching. We hope you found this video helpful.
All right, that was a tough one, huh? Woo. Okay. The pressure of an ideal gas does not depend on, these are blanks to fill in, does not depend on the identity of the gas, it depends on the quantity of the gas. So this is really interesting part, y'all. It doesn't matter what gas I put in there. Okay? It doesn't matter at all. It depends on how much of the gas is in there. So those pressures will be the same, independent of the identity. I think that's interesting. All right, then there's something important. We have to understand something called vapor pressure. It turns out there's a pressure exerted by the vapor which sits on the top of any liquid. So if I have a beaker full of a liquid and I'm trying to use my liquid as a way to push pressure on a gas type of a thing, then I'm going to have to account for that vapor that's at the top of my my water on there, or alcohol, or whatever it is that's in there. The liquid will have a vapor sitting there, any liquid, okay? There's a gas sitting on top of all containers of liquid. This depends on the chemical nature of the liquid. Gasoline has a large vapor pressure. It evaporates very quickly. That vapor up there escapes, actually. You can smell it every time you're putting gas in your car, right? But on water, it's much slower, but it's right above it. So if I could look at my glass of water, there'd be this little layer of water vapor above there.
Did you know that gasoline itself is not flammable or is not combustible? It's the vapors.
It's the vapors, yeah. I think we could make the liquid burn, right?
Well, you can, but
Yeah.
but the vapors.
When you
is
say
what's-
combustible, it's flammable, but it's not it doesn't explode. It's the vapors that explode.
Yeah.
That is true. That's very true. That's why a small amount of gas in a gas can is actually very dangerous, because it fills up there with all those vapors. Okay, vapor pressure and boiling point. So that's what it gets to. I've got that vapor. It's evaporating, right? It's evaporating off of there. It's turning from a liquid to a gas. Another word from turning from a liquid to a gas is boiling, right? It's the evaporation. Vapor pressure also depends on the temperature of the liquid, guys. Shh, Joe. As temperature increases, vapor pressure increases. As temperature goes up, that makes total sense. I'm heating it. I'm going to boil something. I'm going to have much more vapor coming off of it. Then we reach something called the boiling point. The temperature at which the vapor pressure of a liquid is equal to normal atmospheric pressure. That's the official definition of something boiling. It's going to escape from its liquid form and turn into its gas form based on the energy that's being put into there. Something like gasoline, I don't need to add much heat to it. It's already going to be expanding and getting out of there pretty quickly. That's why alcohol evaporates pretty quickly. Okay, so it's got a boiling point that's much lower than water. I believe water's boiling point is one of the highest. 100 degrees C is pretty high. Most other things are going to boil before that. Most other liquids we use in chemistry, at least. All right, so it turns out that we have the boiling point, we have the vapor pressure for each temperature mark for most liquids, namely, it would be water. And I believe this table I'm fixing to show y'all is found in your book.
So the boiling point is why it's easier to boil something at higher
We're gonna get to that.
altitude,
Yeah, because the pressure that's on it. Very good point. We're going to get to that in just a minute.
but the temperature is less.
Correct. All right, so the vapor pressure of water at different temperatures, okay? We're going to see the pressures in kilopascals starting at 0, going all the way up to 100. And at 100, our kilopascals, remember our kilopascals, 1 atmosphere is 101.3. You can see it right there, 101.3. What's the water doing right there? Boiling. All right, but all these other places, look at my pressures, how they're going to change based on the temperature. So if I need these numbers for a mathematical equation, it's going to be a number that's given to you because it's going to come off of a chart. So you don't have to memorize this chart. Good thing, right? Maybe just that last one, right? 101.3 kilopascals equals 1 atmosphere. That's good to know. All right, water boils, here we go, at lower temperatures in the mountains. And that's because the air pressure is much less. All right, so the higher I go up into the mountain and my air pressure decreases, where it's boiling at 100 degrees C down here, it's boiling at 92 degrees C up here. So you're trying to cook something up in the mountains, it's going to take longer. You're boiling your pasta, it's going to take longer because the water's just not as hot up there.
That's why you add salt to it.
Yeah, salt helps, right? Salt's going to help. All right, oh, this reminds me, I wanted to put this plane on here to remind me of this. When you're up in an airplane and you're pressurized cabin and this thing, you never quite get to full 1 atmosphere of pressure. They only pressurize the cabin to about 75% of regular atmospheric pressure. I was surprised by that. I thought maybe some people do get sick on an airplane. Huh?
It doesn't feel any different.
It doesn't to me. Your ears kind of pop a little when you're going up this kind of thing. Yeah, but it is a lower pressure, and since it's a lower pressure, it really is difficult. They said it's one of the hardest things to get on a flight like this is hot tea. because they can't get that water hot enough for your hot tea. You know, with your hot tea, you want that water boiling when it steeps your tea, right? And they have a hard time doing that. That's why they would prefer to serve you cold drinks up
And they can't
in
really
under foam.
put salt in your tea.
Can't really do that. That would not be very good. All right, we're going to watch this cool experiment right here. We're going to manipulate the pressure. And when we do that, so pay attention what happens here, because they are not raising the temperature. They're just going to lower the pressure on water. Check out what happens.
We're going to demonstrate reduced pressure boiling by creating a vacuum in a glass vacuum jar and using an Edwards pump. By using and applying vacuum, we're making water change from liquid to vapor very quickly and very effectively. Water at room temperature is placed into a beaker before putting it into a glass vacuum dome. We now open the vacuum isolation valve. You can soon see the vacuum gauge showing around 20 millibars of pressure. This is significant because it's the vapor pressure of water, and therefore the point at which it will boil at room temperature. At atmospheric pressure, water boils when heated to 100 degrees Celsius. That's because it's the point when water vapor pressure is equal to atmospheric pressure, and water begins to change phase from liquid to vapor. In this demonstration, we don't add any heat, but instead reduce the pressure. When this pressure is equal to the water vapor pressure, the water boils or changes phase, but at a much lower temperature. In fact, the energy for boiling is coming from the water, and consequently its temperature reduces. And as the pressure becomes lower, the water will eventually freeze. You'll see that even when removed from the vacuum chamber, the water remains frozen. A simple process, but one that's widely used in the pharmaceuticals and food
Industries. Yeah. All right, so pretty cool there. Just manipulating the pressure can do that.
So the more they lessen the pressure, eventually will freeze.
Well, because the heat came from the water itself. All right, so because it didn't have heat
Right.
energy from outside, it just used all the energy inside of it, which made it go to its solid form, right? Because all the energy was taken out of it. Pretty cool.
It's like boiling something.
All right, Dalton's law summary. This law tells us that the total pressure of a mixture is simply the sum of the individual pressures of the gases. Vapor pressure is the pressure exerted by the vapor that sits atop any liquid. The vapor pressure of any liquid increases with increasing temperature. To determine the liquid's vapor pressure, we need to know the identity of the gas and the temperature. Now, identity is underlined. Does that mean it's a blank to fill in? Or did I just want to emphasize it? No, not there? Okay, very good. All right, example 11.2. A chemist produces hydrogen gas in an experiment and collects the gas in the presence of water. If the total pressure of gas collected was 1.115 atmospheres and the temperature was 26 degrees C, what was the pressure of hydrogen gas collected? All right, there's a mixture of hydrogen gas and water vapor. So, PT is the pressure of the hydrogen plus the pressure of the water vapor. And check the table. I don't have that. I meant to write that down. But at that temperature, 25.2 torr. Oh, we're using torr in this one. Okay. I have atmosphere there. Oh, we have to turn torr to atmosphere. Why don't we just look up atmosphere? Here it is. It's because it gave me atmospheres here. We have to keep those units the same. So I go from torr to atmospheres. So my number is 0.0332 atmospheres at 26 degrees C. Now use Dalton's. 1.115 atmosphere, which is my total, is the pressure of hydrogen plus this number we just calculated, and we turn those around and we end up with 1.082 atmospheres. Okay, so a little bit of gymnastics there, but not bad, not bad. Hopefully I don't give it to you in torr. Did you notice also in that video he said millibars? That's another one we don't even talk about. It's called bars. And we don't talk about that one. So I don't know why we don't bring it up. We're just going to be talking about these three here. It's just another way of measuring pressure. Okay, what about, moles? No. That's a nasty mole, for sure. Yeah. Okay, now this is interesting, y'all. Listen. Remember, we're going to be looking at some something called the mole fraction. It is the number of moles of solvent per moles of solution, or of solute per moles of solution. That was what we did with our liquids, and now we're going to see it's very similar with our gases. So here's our Dalton's law and the mole fraction. The mole fraction is called X. Do you have to write this one down? This is important. Number of moles of the component, solute or solvent, and the total number of moles in the mixture. So we're going to calculate the total number of moles, and then we're going to get each individual mole fraction by putting it over that number, okay? The mole fraction tells us the fractional part of the component in relation to the entire mixture. It's dimensionless, it won't have any units at the end. The partial pressure of any gas in a mixture depends on the mole fraction of that gas and the total pressure of the gas mixture. So we're taking Dalton's law of partial pressures, and then we're just putting it here and finding that in the moles, okay? All right, example 11.3, here we go. A mixture of gases contains 3.0 moles of oxygen, 5.0 moles of nitrogen, and 1.0 mole of neon. What is the mole fraction? That's all it's asking for. What is the mole fraction? Okay, so what are the total number of moles? 3 plus 5 plus 1 equals, I have a grand total of 9 moles. Yeah? Okay. Now use the mole fraction. This is very easy. If I want to find X, mole fraction of O2, I'm going to take, and N2 and then neon right here. I'm going to take 3 divided by 9. Moles cancel, 0.33. N2, 5 divided by 9, 0.56. And neon, 1 divided by 9, 0.11. And that is all you have to do on those. If you already have moles, that's all you have to do. But sometimes, guess what? We're not going to have moles. We're going to have to find the moles. We're going to have to calculate the moles. All right. Applications of Dalton's law. We have rearrangements here. All right, we're looking at our that's our mole fraction. Mole fraction right there. Rearrangement, solve for mole fraction right here. Okay, we're just rearranging that. All right, we're in part B. Okay, putting everything together. Oh no, we have grams. Yikes. A gas mixture contains 40 grams of carbon monoxide, 10 grams of nitrogen dioxide. If the total pressure of this gas mixture is 1.2 atmospheres, what is the partial pressure of each individual gas? All right, here we go. I'm going to restate the question right there so we have all of our data. Here's what I need you to understand, that 1.2 atmosphere right there, the total pressure right there, we're calling that P2. And we're looking for partial pressures of each of the gases. First, we have to convert grams to moles. Everybody comfortable doing grams to moles? Yes. All right, we have our 40 over 1 because that was given to us. We get our 28 from the periodic chart of the elements. We realize that we have 1.43 moles of carbon monoxide. We do our 10, which was given to us, over 1, our 1 over 46 from the periodic chart of the elements. We get 0.217 moles of NO2. And next, we're going to calculate the mole fractions using that thing right there. All right, so we add them together. We end up with total moles of 1.65. And now we're going to, for carbon monoxide, we're going to take this number that we calculated and put it over this number that we calculated. So 1.43 over 1.65, we have 0.867. We're looking at P1 there. And we're going to do it again for NO2. Also P1, because remember, we're going to add those together. And now we're going to get our pressure here with our atmospheres, right? Our PT equals P1 plus P2. We have our 1 atmosphere and our 6.16 atmospheres right here. And, oh, but wait, there's more. Okay, but wait, there's more. We're not done. I think we're done with the problem, right? Is that all we wanted? What is it? We asked for the partial pressures, and there they are, 1 and 0.16. And we were working in atmospheres. We had atmospheres for everything, so we're good. So I think, but wait, there's more means to do with philosophical. Those are the partial pressures. Our total, P2. All right, good? course, this is in your book. But wait, there's more.
Why?
The ideal gas law. Since it's difficult to measure the mass of gases, like 40 grams, for instance, I'm like, really, y'all? We need an easier way to relate moles of gas to the things we can measure more easily, like pressure. We can measure that more easily. All right, the ideal gas law does this. So, we have Boyle's law, we have Charles' law. This, we didn't actually talk about Avogadro's law right here, because we also have Gay-Lussac's law, which we've talked about previously. All of these play into this to make the ideal gas law. Avogadro's law was really just restated in each one of those two laws. All right, so this is probably the most important math equation you need for today, for this module. PV equals nRT. So what does this give me? It gives me pressure, volume, number of moles. Little n stands for number of moles, okay? R stands for something called the gas constant. Guess what? When you see something that's called a constant, right, what does that mean?
It's not changing.
It's not going to change. So we have to either be given it, either it's given to you or you memorize it, okay? And then T, of course, is temperature, which will be changing. All right, so PV equals nRT. This is our key equation. So study this one. So really this one and this one. And don't forget that. Always go.
What about Dalton's law?
Well, yeah, you need to know that too. I'm just talking about for equations. Yeah, the P1, P2, that's so easy. That's addition. I didn't even mention that. All right, ideal gas law P, we have our V is volume, N is mole. Here is R. R equals 0.0821 liters atmosphere over mole K. Wow.
Not confusing.
Temperature in Kelvin, of course. Obviously. All right, so this is going to be our ideal gas law, and we use this when we have the conditions of an ideal gas. Let's see what Professor Dave has to say about it.
Call our definition of a gas as the phase of matter where atoms of a substance are in motion and fill their container. If we make a couple simplifying assumptions about gases, we can make some easy predictions. Those are that 1, particles of a gas are dimensionless points in random motion, and the identity of the gas is irrelevant. Could be anything. And 2, that the particles don't interact apart from elastic collisions, bouncing off one another like balls on a pool table. These things aren't completely true, but they make the math easy and surprisingly accurate. So these kinds of samples are called ideal gases. When examining an ideal gas, we want to be able to discuss 4 variables. 1, pressure. This is the force the gas is exerting on its container, or rather, how much the particles are hitting the sides. 2, temperature. This is the amount of heat energy available to be transferred into kinetic energy of motion. The higher the temperature, the faster the particles move. 3, volume. How big is the container? And 4, moles. How many particles are there in the container? So, how many particles, how big is the container, how fast are the particles moving, and how often do they hit the sides? As it turns out, these variables depend on one another in interesting ways that have been formulated into laws. Let's look at a piston. While keeping the moles and temperature the same, in other words, the same number of particles moving at the same speed, if we compress the volume, the pressure must go up. The particles will be hitting the sides more often because there is less distance to travel to hit a side. That means that pressure and volume are inversely proportional. If one goes down, the other goes up.
That's Boyle.
This is expressed in Boyle's law. P1V1 equals P2V2. If we double one variable, we have to cut the other one in half in order to keep this equation valid. Volume and temperature are also related. If we have gas in a balloon and we heat it up, the particles will move more quickly. In order to keep pressure constant, or hit the sides with the same frequency, the volume will have to expand. This means that volume and temperature are directly proportional. If one doubles, the other must double. This is expressed in Charles' law. When we do calculations with temperature, we must always use an absolute temperature scale called the Kelvin scale. 1 degree Kelvin is the same magnitude as 1 degree Celsius. But 0 Kelvin is absolute zero, the lowest temperature possible, a complete absence of heat energy. This helps us avoid weird mathematical issues that would arise if we were doing a calculation involving a negative or 0 temperature. To get Kelvin from Celsius, just add 273. To go the other way, subtract. The combined gas law is like a combination of Boyle's and Charles. Avogadro's law says that equal volumes of gases at the same temperature and pressure contain the same number of molecules. Specifically, that 1 mole of ideal gas occupies 22.4 liters at standard temperature and pressure, regardless of the identity of the gas. Lastly, all the variables correlate in one equation called the ideal gas law. This also contains the gas constant R, which makes these calculations intelligible in our man-made units. There are a number of values for R depending on the units, but we will predominantly use this one. This equation is useful when we aren't looking at a change, but just to know the values of all 4 variables at once, like in this case. We could know the pressure, temperature, and volume of a gas, and quickly calculate how many moles of particles must be in the sample. So if you were looking at a sample of gas and you have 3 of the 4 variables, you can solve for the 4th using the ideal gas law. If you are given some initial conditions as well as some final conditions, you can use one of the other laws to find the other information. Just plug in what you know and solve for what you don't. Let's check comprehension.
All right, we don't need to do that. We have our own stuff. Okay, so here we go. Rearrange for different values. Once again, that's just a little bit of algebra there, and of course, remember to use Kelvin scale. Okay. All right, example 11.5. A gas is in a 12.2 liter container at a pressure of 13.5 atmospheres and a temperature of 25 degrees C. How many moles? So what are we looking for?
Moles.
N. We're looking for N. All right, we're looking for N. So N equals this, PV over RT. We're going to convert to Kelvin, and we're going to see, we're going to pull these numbers in, and we're going to see we have 6.73 moles. Voila. That easy. Pretty simple. So once again, just practicing these problems will help you get them correct on your quiz next week. If I remember properly, I can't promise this, I can't guarantee, but I'm pretty sure I give you R. Okay. And so you have to memorize, but go ahead and memorize it. Just get it. Ideal gas law and no. It's stoichiometry. If we can find a way to determine the number of moles of gas we have, we can do stoichiometry on it. Hooray. Right, yeah, we can stop now. Okay, an automobile engine, the gasoline, C6H18, is burned to make gaseous CO2 and H2O. That is a combustion reaction. A gallon of octane has a mass of about 3.2 times 10 to the 3 grams. If a gallon of octane is burned in excess oxygen, at pressure 1 atmosphere and temperature 180 degrees C, how many liters of CO2 are produced? So here's our equation. What's the very first thing we have to do? We have to balance that. Does anybody want to balance this one?
Yes.
I'll give you a 2. I think we balanced this one before, right?
Pretty sure now.
And a 25, and a 16, and an 18. Okay, so none of our stoichiometric coefficients are the same. That means when we're going to relate these guys, we're going to have to relate them based on their stoichiometric coefficient. So my point being, in a case like this, we're going to want to do factor label method no matter what, okay? Because we won't forget one of those little numbers on something. All right, so there the problem is written down very small over here to the right, and then our equation is going to be up here at the top, I believe. Yeah, there it is. So relating moles to each other, look at the coefficients. All right, what are we asking for? How many liters of CO2 are produced? Okay. I went ahead and changed our 3 times 10 to the whatever to 3,200 grams. Okay, just, it's easier for me that way. Okay, and then I have my grams per mole from the periodic chart of the elements. So I have 28 moles of octane. All right, that's good. So I take my moles and my moles of carbon. Where did I get that 16 from? Right here. Now here's why I want you to do factor label method, because it'd be very easy to forget that too. Where'd that 2 come from? Right there. Okay? It's going to be easy to forget that one if you don't do it like this. We had our 28 here over 1. We have 224 moles of CO2. What's it asked us for? How many liters of CO2? Okay, so PV equals nRT. And we're looking for volume. So we rearrange it like that. We plug in all of our numbers, including the one we just calculated. What's this number? Where'd this come from?
It's the constant.
That's the constant. That's R. Okay? And then, did we already have it in Kelvin?
No.
Oh, I converted right there in this little tiny square right here. You can see the conversion right there. So that's in Kelvin over 1 atmosphere. And we're going to see the answer is 8.2 times 10 to the 3 liters, or 8,200 liters. So really our PV equals nRT is a very powerful tool since we're so good at finding our moles. Okay. All right. So, we're at the end, y'all. Here we go. This is at the end. You're going to say this. The combined gas law. When do we use these different things? Okay. When are we going to use these things? We're going to use the combined gas law, the most powerful of the ones we've had today. When you need to know the temperature and pressure you place a gas in. When you need to know the temperature and pressure to place a gas in a container. That's a weird way of saying that. You use that when you need to know the temperature and pressure to place a gas. We're going to use Dalton's law of partial pressures when we need to know the pressure of an individual gas. We're going to need the mole fraction when we need to know the percent amount of an individual gas in the mixture, just one of those pressures. And our ideal gas law, did I say the top one was the most useful? I think it's really this one's the most useful. The ideal gas law, we use this when you need to know what stoichiometry can tell you, such as volume or grams of a gas produced in a chemical reaction.
Yes, it means what stoichiometry can't tell you, right? Instead of can tell you.
No, I think stoichiometry is telling us that, right? Because it's giving those coefficients. And then, therefore, knowing those coefficients, we relate them like that last problem. I'm going to get grams through stoichiometry, right?
Right. But like when we were looking for the volume in the last one, we couldn't find that through stoichiometry. We had to use that problem and flip it around.
And flip it around.
Maybe
Okay.
that's what they mean.
If
by
that's the way if
stoichiometry.
you're looking at it from that direction, okay. I was looking at it from the other direction, saying the coefficients helped me. Believe it or not. All right, gang, and so that's it for the lecture. And next week we'll have our lab and our quiz. All right, very good. Study.